Do we live in a hologram? Physicists claim they have discovered evidence that the universe might be a hologram. When it comes to the universe, the idea is that all the physics that happens in the world is, in a sense, generated by happenings on a two-dimensional boundary surface. The holographic principle is a tenet of string theories and a supposed property of quantum gravity that states that the description of a volume of space can be thought of as encoded on a lower dimensional boundary to the region, such as a light-like boundary like a gravitational horizon. First proposed by Gerard T. Hooft, it was given a precise string theory interpretation by Leonard Susskind, who combined his ideas with previous ones of T. Hooft and Charles Thorne. As pointed out by Raphael Busso, Thorne observed in 1978 that string theory admits a lower dimensional description in which gravity emerges from it in what would now be called a holographic way. The prime example of holography is the ADS/CFT correspondence. The holographic principle states that the entropy of ordinary mass, not just black holes, is also proportional to surface area and not volume, that volume itself is illusory and the universe is really a hologram which is isomorphic to the information inscribed on the surface of its boundary. A holographic universe means information that makes up what we perceive as a 3D reality is stored on a 2D surface, including time. This means, essentially, everything you see and experience is an illusion. While theories of holographic universes have been around since the 1990s, the latest study, published in the journal Physical Review Letters, contains the first proof. In this sketch of the timeline of the holographic universe, time runs from left to right. The far left shows the holographic phase and is blurry because space and time are not yet well defined. Patterns imprinted in it carry information about the very early universe and seed the development of structures of stars and galaxies in the late time universe, far right. The fabric of space and time is widely believed by physicists to be emergent, stitched out of quantum threads according to an unknown pattern. And for 22 years, they've had a toy model of how emergent space-time can work, a theoretical universe in a bottle, as its discoverer. The anti-de Sitter/conformal field theory correspondence, sometimes called Maldacena duality or gauge/gravity duality, is a conjectured relationship between two kinds of physical theories. On one side are anti-de Sitter spaces, ADS, which are used in theories of quantum gravity, formulated in terms of string theory or M theory. On the other side of the correspondence are conformal field theories, CFT, which are quantum field theories, including theories similar to the Yang-Mills theories that describe elementary particles. The holographic principle was inspired by black hole thermodynamics, which conjectures that the maximal entropy in any region scales with the radius squared, and not cubed as might be expected. In the case of a black hole, the insight was that the informational content of all the objects that have fallen into the hole might be entirely contained in surface fluctuations of the event horizon. The existence of such solutions conflicts with the holographic interpretation, and their effects in a quantum theory of gravity including the holographic principle are not yet fully understood. So do we live in a hologram? Even if the ADS-CFT link proved fruitful for tackling quantum gravity, if we were able to find a way to navigate the challenges and make this technique relevant for the universe we live in, it doesn't mean that we actually live in a hologram. It's a mistake to make the jump from CFT provides a handy way to solve gravitational problems to our universe with gravity in 3 dimensions is an illusion, and we really live in a 2-dimensional boundary with no gravity. A mathematical contrivance, as handy as it may be, doesn't necessarily dictate our views of the fundamental nature of reality. If holographic principles are useful for solving problems, it doesn't necessarily mean that we live in a hologram. And even if we did live in a hologram, we wouldn't necessarily be able to tell the difference anyway.